This is Yi from PingCAP. I'm on the TiKV storage team. Today, I'm going to share about running TiDB on the cloud disk or in AWS, the EBS service. And for our TiDB cloud service, which we provide TiDB as a service to our users, we are switching from using local disk to cloud disk, which is the EBS. And for our on-premise users who deploy TiDB on the cloud, we are also recommending them to use the cloud disk. And today I'm going to share why we prefer a cloud disk over local disk, and what the performance would be like when running TiDB on EBS, and also what are the optimizations that we have done to improve the TiDB's performance on EBS. So before digging into EBS, I would like to talk more about TiDB itself, because the reason why we prefer EBS over local disk is more TiDB specific. Yeah. So this shows an overall picture of TiDB cluster. TiDB is a distributed database, which is MySQL compatible, and it has several components inside a class inside TiDB cluster. So there is a TiDB component which handles the SQL processing and being the compute node in the cluster, and there is PD, which provides the metadata service and also provides TSO service and so on and so forth, and it also controls the load balancing for TiKV. And then we have TiKV, which provides a distributed key value service, and being the storage node in the cluster, mostly handling the transaction type of queries. And to handle analytical type of queries, we can also add the TiFlash node, which have a columnar store, which is better at handling the analytical type of queries. But for today, we'll just focus on TiKV. So for TiKV, it provides a distributed key value service, and for the full key range, it is split into small ranges. We call them regions, and each region is the unit of replication and load balancing. And normally, with each region will have 3 replicas, and those replicas will be distributed among all the TiKV nodes. And all these replicas will, for one region, will form a rough group. And so because for one region there will not be 2 replicas located on one single TiKV node. So whenever we lose one TiKV node, for all the regions on this node, there will still be 2 replicas located on the other live TiKV nodes. So in this way, those replicas can still provide serve traffic. So in this way, TiKV provide a high availability. So this is about losing one TiKV node. But how about if we lose 2 TiKV nodes simultaneously? Yeah. So here is an example showing what happens if we lose 2 TiKV nodes simultaneously. So here we have 4 TiKV nodes in this cluster, and we have the node 1 and node 4 go down simultaneously. And there will be some regions that have 2 replicas located on both of these down TiKV nodes. For example, here we have region 1, region 4, and region 5. Both have all of them have 2 regions, two replicas on these two down TiKV nodes. As a result, those regions will lose the majority of the replicas. And by design, because we are using ROC, the consensus protocol, losing majority means that those regions, those part of data are unavailable. And what's more, in this scenario, the cluster wouldn't be able to recover themselves, and it needs human intervention to bring the cluster back up. So yeah, so here is the problem. So by design, because we are using consensus protocol for replication, when we're losing majority of the replica, and then it will lead to unavailable to some part of the data. And in TiKV, because of the constant load balancing, we are running the regions are mostly randomly scattered on different TiKV nodes. And so when we lose two TiKV nodes simultaneously, there is a high probability that there are some regions that have two replicas located on these two failing TiKV nodes, and which will cause unavailable for some part of the data. And that's the problem. And of course, we could consider to use a technique called copy set, which will allow us to cleverly place those regions on the TiKV nodes, so that when we have two failing TiKV nodes, there will be a lower chance that it causes unavailability. But on the cloud, there are another similar problem that even with copy set, it couldn't be solved. So on the cloud, we usually will deploy across three availability zones or AZs, and so and also by using a feature in TiDB called a placement rule, we could place all the replicas of a region across different availability zones. So even when one AZ completely go down, for all the regions, we still have two replicas located on the other availability zones, and as such, they can keep serving traffic. But what if, along with one AZ down, we have another node in another AZ goes down? So in this example, we are showing that the AZ1 is down, but the node 3, TiKV node 3 on AZ2 is also down. In this case, we have the region 1 and region 3 have the majority goes out, and it couldn't serve traffic. And we call this type of problem AZ+1 failure. And in this case, we still have we're still left with the cluster that is unavailable and needs human intervention to bring the cluster back up. You may think that this type of failure may happen really rare. How come when there is a whole AZ goes down and there is more machines go down? But we actually we actually saw one in production, and because that production cluster is really big, and it takes a really long time for us to and a lot of human effort to bring this cluster back up, and it was really bad. So we want to solve this problem, and so that's why that's where the cloud or EBS come into the picture. So EBS stands for Elastic Block Store, which is the cloud disk on AWS. It behaves just like a normal block device or disk, and EBS volume can attach to one EC2 instance as a disk. But it has a nice feature that the data are persistent, independent to the EC2 instance, which means that when the EC2 instance fails, the data stored on the corresponding EBS volume is still there, and we can easily remount this EBS volume to a new EC2 instance, and the data is not lost. And under the hood, so EBS have, I believe, 2 replicas within an AZ, so it have a higher availability compared to lower failure rate compared to EC2 instance. So by comparing using local disk and EBS, so when we are using local disk to store our data on EC2, when one EC2 instance fails, the data stored on the node are also lost. And so in this case, TiKV will need to re-replicate the losing replicas in the background, and it takes time and the CPU and IO resources. And if before the replication is done, there is another EC2 instance fail, then it will lead to unavailability. It will lead to unavailable because of the issues that we just described. With EC2 with EBS, the EBS failure happen far less often, and when one EC2 instance fail, the data in the EBS volume is still there, and with the help of Kubernetes, we can automatically remount this EBS volume to a new EC2 instance, and the data will immediately show up again, and so we don't even need to re-replicate those data, and it avoids the unavailable issue that we just described. So with EBS we can mitigate the issue that the unavailable issue, for example the AZ+1 issue. But how about the performance? Yeah. So to figure this out, we run some simple FIO tests on the EBS volumes, and we want to compare the performance between EBS and the local disk, and also there are several different volume types that EBS provides, namely GP2, GP3, IO1, IO2, and those different EBS volume types provide different performance characteristics, and also they come with different pricing. So we want to have some benchmark to figure out which type of EBS volume we want to use. So here we are showing a single thread FIO test with 4K IO and fixed 1000 IOPS, and here we want to see the latency across different disk types, and here we can see compared to all the EBS volume types, the local disk outperform them in terms of latency by several times. And here is another benchmark with multiple threads, again with 4K IO size and 3000 IOPS in total, and the local disk is outperform all the EBS volume types by several times in terms of latency. So but looking at this benchmark, you may think that the EBS performs poorly, and if we run TiDB on EBS, we will end up with very poor performance. There is another set of benchmark we run that shows a slightly different story. So we construct the FIO test so that it will simulate a mixed workload that simulates what TiKV does, and it will have several threads doing small writes and several threads doing small reads, and there will be some threads doing large writes to simulate the compaction. And so with this benchmark, we'll see that as we have a mix of workload, and especially when we have more intense workload against the disk, the latency gap between EBS and the local disk actually becomes smaller. And here you can see that on the rightmost side, the latency difference between EBS volumes and local disk is less than 2x. So it shows that when we have a moderate workload on TiDB or TiKV, then the performance gap between using EBS and using local disk will not be that much. Yeah. So we continue to run some actual benchmarks on TiDB, and again here we are using the TPCC benchmark, and we run it against TiDB, and when TiDB is running on different EBS volume types, and we compare to the TiDB that using a local disk, and we use we test TPCC with different number of threads to simulate different type of workload, and so with a smaller number of threads which simulates lighter workload, we actually see in some case the local disk indeed still have advantage, especially when compared to the GB3 volume type that we plan to use. When using local disk, it still have a lower latency. But when we have a heavier workload, for example, when we have 200 or 800 threads, TPCC client threads, the EBS actually perform better. The reason is that TiKV is CPU bounded in this benchmark, and actually under many other type of workloads, and so the disk latency will represent a smaller ratio of the overall performance, and because they're on AWS, there are more EC2 instance type that support EBS than the with local disk. We only have the I3 or the C5 instance type that to choose from, and those instance types have a less powerful CPU. And so with EBS, we could choose to use more instance type with a more powerful CPU, and so to achieve a better performance. So as a result, with some workloads, when with using EBS, we actually can achieve better performance, and the performance disadvantage when the workload is lighter. That's the trade-off we are willing to make. And so we switch from using local disk to use EBS, and over time we have more and more users that using the cloud disk, and we are gaining more experience with the EBS, and we notice there are some optimizations that we can do to improve the performance when running TiDB on EBS. The first thing is that since we are using RocksDB as the storage engine in TiKV, RocksDB will run the compaction in the background, and the compaction is when the compaction kicks in, it usually is up a lot of I/O throughput. And with EBS, the I/O throughput is limited, and we for us we usually use EBS volume with several hundred megabytes per second throughput limit. And when those compaction kicks in and it eats up the I/O throughput, it will hurt the foreground I/O latency. So as a result, we work on two optimization to mitigate the problem. So one is the improved RocksDB compaction rate limiter, which will monitor the history of flush and compaction I/O that we have, and use that to smooth the I/O for the background compaction. And right, so by doing so, we will make the compaction runs instead of having a spiky compaction, we'll make it more run more smooth, and reduce its impact on the foreground I/O. And yeah, and another thing we do is we add the overall TiKV I/O rate limiter, which monitors all the I/Os, including the background I/O, the compaction I/O, and the foreground I/O that we are doing read and write, and also all the I/O that we issue for load balancing or backup, etc. And so we assign priority to those I/Os, and so if we are hitting the EBS throughput limit, we'll throttle the background I/O and make room for the foreground I/O. And with the help of these two optimizations, and as we can see from the picture on the right, when we have the relimiter enabled, the write throughput becomes much more stable. On the right, that's without a relimiter, and you can see that the write throughput become very unstable, very spiky. So yeah, so this is for the IO relimiter. And another thing we notice for EBS is that over time it can have performance jitter, and that's because under the hood it may have some failure, and sometimes it need to re-replicate data, and sometimes there will be network congestions, and that have all happened behind the scene, but it will shows up in the for us as a performance downgrade for some of the EBS volumes, and sometimes especially when we have a larger cluster, we'll notice this phenomenon more often, and usually it might just affect one TiKV node at a time, but sometimes for some of the use cases we have, such kind of performance downgrade can have a cluster-wide impact. For example, for one scenario where we have a data replication scenario running in the upstream, and where this replication will apply the change from upstream sequentially, and below is spread evenly on all the TiKV nodes. When the EBS volume on one of the TiKV nodes become very slow, and this TiKV node also become very slow, this single slow node become the bottleneck of the whole cluster, and in combined with other issues we have, it in this case it actually bring the TiDB QPS down to almost zero. And so to mitigate this issue, we introduced a mechanism called slow node eviction. And the idea is that TiKV will periodically send itself a sample request to measure its own performance and report the result to PD. And PD will collect those samples and compute a score to decide if a TiKV node becomes slow. And if that's the case, then PD will trigger an evict leader scheduler on the slow node to basically remove it from the cluster. And so yeah, here are some pictures. On the top is a screenshot we take from the metrics on one of our production cluster, and you can see for this node the EBS volume becomes slower than normal for about 2 hours, and yeah, and it causes problem. And in the bottom it shows a simulation of the slow node eviction mechanism, and in here we are showing that when we start the simulation, we will simulate we should simulate the case where one TiKV node become extremely slow, and you can see here the overall QPS of the cluster drops. And then after a few minutes, the slow eviction kicks in, and it brings the QPS back up to normal. Yeah. So yeah, and so that's the two major optimizations that we have done on TiKV to make TiDB run better when using the cloud-based EBS. And there are actually some ongoing projects we hope to get done soon. And so one thing is the rough engine. So for now, for each of the TiKV nodes, we have two RocksDB instances, one to store the rough log and one to store the data. And for the one that store rough log, we actually see the background compaction kicks in often, and it consumes a lot of IO throughput. And as I have mentioned, the EBS usually have a low throughput limit. So we want to reduce the overall IO throughput consumption by TiKV. So we are replacing this RocksDB instance with a custom built rough log storage called rough engine, and instead of storing the rough log as key value pairs in RocksDB, we now with rough engine we now store the rough log in log files, and with a custom GC routine that is more efficient than the RocksDB compression, we actually see in some of the benchmark we reduce the overall TiKV throughput by 40%, which is a lot. Yeah, we hope to have the rough engine getting into the GA status in the next release, but yeah, which it means in a few months. And another bigger changes that we are making is the multi RocksDB changes. So for now, for the data on the TiKV node, we have one single RocksDB instance to store the data. And with the multi RocksDB design, we are changing to use one RocksDB instance to store the data for one region or the key sub-key ranges for TiKV, and essentially sharding this single RocksDB instance. And by doing so, we will greatly reduce the write application by this single gigantic RocksDB, and which will also help to reduce the overall TiKV IO throughput consumption. And it also has other benefits like it will enable us to do a physical snapshot when we try to run load balance and then move one region to another TiKV node. And it also because we reduce the size of RocksDB, we will reduce the global mutex contention in RocksDB. Yeah, and for this project, we hope we can get it done by next year. And so yeah, that's all I want to share today. Yeah. Feel free if you have any question. Yeah.
Yep. Thank you very much. That was an excellent presentation. We really appreciate it. We do have a bunch of questions that came into the chat while you were talking, and so we'll run through them really quickly. The first one that came in is, did you find any specific EBS storage type, GB2, 3, IO1, or IO2, was better than any of the other ones, or did they all have similar performance?
They do have different performance characteristics. For example, the IO2 or someone mentioned in the chat, the IO2 block express, of course have the best performance, but is more costly, and we incline to use the the cheaper GP2 or GP3 in the volume types, and for the GP2 volume types under a smaller workload, it will have a lower latency, but it will have a higher tail latency when we have a more intense workload. And also it has a limited IO throughput of 250 megabytes per second, which is not configurable, which we consider is bad. And for the GP3 volume types, and they tend to have a more stable latency, despite the latency when you only have very light workload, the latency will be higher compared to GP2, but it comes with a configurable IO bandwidth. So we end up using the GP3 volume types. Yeah.
Okay. And to follow up that, actually, Chris asked the question, so are there any plans to test the EBS IO2 block express that Amazon has just recently released?
Right. So yeah. So we are aware of the IO2 block express type, and we are excited about it. But right now the IO2 block express is only limited to the R5B EC2 instance type, and that instance type, per our experience, is low in stock. So sometimes when we're creating a cluster, we won't have enough R5B instance available for us to create a cluster. So it's not super practical right now, but well, we do feel the IO2 block express very exciting to try.
Yeah, I'm not surprised about about R5B being not as available as the rest until they expand it. Okay, so Andrew asked this question: Databricks separated WoW and data disks, the WoW and the data disks for better performance. Did you benchmark the two separately, or did you benchmark them together?
For the benchmark, I'm showing we are having the write hello and the data stored on the same one single disk. We do have benchmark that to see what if we have two EBS volume, one having the write hello, one having the data, and we on AWS EBS we actually see around 10% of throughput improvement, and then some and a slightly more stable tail latency when we are having such a setup. But so that's because the EBS have okay-ish performance compared to the Azure cloud disk. So we are not seeing that much performance difference compared to when we have Azure like in the Databricks case.
Yeah, sure. Yeah, okay. That makes some sense. So the next question actually come from Hanu. He said he is a little confused by why R5B with local disk would be bad in performance and R5B with EBS. Could you explain the difference between the two? Why the EBS is better? Why? Can you basically just clarify that a little bit?
Actually, with R5B, it doesn't provide local disk. So here the comparison is between using R5B plus. Here is using R5B plus EBS compared to using i3 with local disk. So the i3 have a less powerful CPU. And in this benchmark, the TiKV is CPU bounded. So as a result, with the R5B plus EBS, we have better throughput.
Sure. Okay. Yeah, I'm gonna just skip around a little bit here. I'm gonna go to Andrew Wang, who asked. So you had a section where you talked about the failures with the with where TiDB is running on a node, and all of a sudden that node would start to freeze up. He asked, how does the TiDB handle gray failures? For example, a node that intermittently is slow or is slow only for a few minutes at a time. Does the system that you set up also deal with that as well, or would it be able to find those?
Yeah. So yeah, as you can see, so the the only mechanism we currently have to battle the gray failure just this slow node eviction mechanism. And as you can see from this picture, it takes a few minutes to kick in because we want to avoid the false positive. So if there is a gray failure lasting for just a few minutes, this mechanism wouldn't be able to help.
Sure. Okay. And then a couple more questions have come in. The first one is from Pen Zhang. Have you benchmarked the block storage services from any other clouds, or was this just specifically done on Amazon?
We also did some benchmark on against, for example, the cloud is on GCP and also on Google Cloud, and also the cloud is provided by Azure, and we see that the EBS on AWS EBS actually provides the best performance, and also when say, for example, when it says that you are having a EBS volume with say 300 megabytes per second throughput, it do provide you 300 megabytes per second throughput. And with the cloudies for Azure and GCP and we can achieve the throughut claim by the cloud vendor. So and the performance is of those GCP and Azure cloudies are much less stable than EBS. Yeah, but still we have fewer experience with GCP and Azure. So yeah, we still need more work to figure out. Yeah.
Sure. Yeah. So my last question. And I have one question that came from Rui. I think he asked this question in context while you were in the middle of talking through a slide. And he asked this question that since TiKV is CPU bounded in this case, it seems like using EPS performs better is partly because more resources are available from EBS. I think that you were talking about that at one point about TiKV being CPU bounded. Can you just can you talk about whether EBS performs better because there are more resources available? So I think the question is actually it's a little confusing. I think what he was basically saying is that I think if I translate that question, this particular slide you talked about it being CPU bound in this benchmark, right? And then EBS provided better performance. You said that in your slides. I think he was asking like, so would it be why is EBS providing better performance there when you're CPU bounded? Could you basically just kind of explain that a little bit more?
Right. Yeah. So yes. By saying the CPU is bounded in this case, of course, the I/O is not bounded. So we are not hitting, for example, the throughput limit, the I/O/PS limit of the corresponding EBS volume we are using. So in this case, the EBS volumes still have good enough performance. Okay. Although the latency may be slightly higher compared to the I/O on the local disk then, but that's not the bottleneck. So yeah.
Okay. We have time for one more question, and we did get one from Ashwini. The questions are starting to get better. They're beginning to get a little bit more. They're wider, more divergent, and this one, of course, is about talks about cold storage instead of using. It's kind of the opposite of performance tuning. This is about cost savings. But they actually asked if there were any benchmarks or any information on using cold storage like S3 to take cold data or to take some of the data basically off of out of TiKV, especially the data that doesn't change, and moving it to S3 to lower the storage cost. If you guys have considered that, or have you done any benchmarks on it at all? Or
we actually consider using S3, but so that would be a larger architectural changes for us, and also there are different performance characteristics for S3. For example, if you just want to do a small I/O on the S3, then it's of course less efficient and more costly because it's charged by IOPS by the number of queries but we do considering some architectural changes that allow us to use S3. Okay.
Yep. Great. Well, yep. Yi, thank you very much for your time. That has been excellent. I think that's the end of all of our questions for this evening. So, yep. Thank you very much again. That was a very excellent presentation. So,
cool. Thanks, Jonathan.